Okay. Up until now, we've been mainly talking about the top part of the engine, the pistons, rings, cylinder, and I wanted to kind of revisit one thing in case we haven't covered it yet, was when you are performing a top overhaul, you are dealing with the cylinders, pistons, rings, and those things. You can class or sign off in the logbooks what is considered to be in returning to service an engine that's had a top overhaul. So if you've done all the requirements and procedures, you can sign that off as being a top overhaul. If you're doing the whole engine, that is referred to as a major overhaul. So again, don't confuse when you hear that word major. Doesn't require an IA or repair station or something like that in 337 forms to return it to service. It just simply they're using the word major, meaning the whole engine, major overhaul. So those two categories, major overhaul, top overhaul. So what's the minimum license required to return the engine to service after it's had a major overhaul? If it didn't have any major repairs, would be a power plant license. Okay, so first going to talk a little bit about the crankshaft, and we'll turn this around and let you have a peek of the crankshaft here. So starting from up front where you've got your flange, and then of course that's where your propeller hooks to, and then you got your slinger ring here. So this helps control oil that's in the engine. In fact, as it's quite often getting ready to go out the crankcase breather, this helps to keep oil from flowing out the crankcase breather. Then we are up here where this would be our number one main bearing would sit here. So if you have like a fixed pitch prop where there'd be a plug up in the front of that expansion plug we showed you in the one picture, you'd have your main bearing that would sit here. If you have a constant speed prop, you would have these type of bearings where your number one and two bearing are hooked together, and then the oil comes from the governor, comes in these holes right here, and then it enters into the inside of the crankshaft. So that expansion plug on a constant speed prop would not be in there. There'd be a plug back here. So the oil goes from in there, and of course is surrounding the crankshaft in this recessed area here, and then goes in that hole there's in the tube and fills the inside of the crankshaft. And so you got your pressurized oil from the oil galleries feeding oil into the main. You'll see a hole that's here, and a hole that's there, and then you've got your governor boost oil pressure goes in the center. Okay, and then of course you got your 1, 2, 3, number 4 main. So that gets a little confusing sometimes when you are mounting the crankshaft in a V block, and they say to mount the crankshaft at 1 and 4. Tends to you kind of think, oh, this is number 1, this is number 2. So there's actually 1, 2, 3, 4 on the mains. Okay, and then taking a look at our rod journal, or Continental calls it a crank pin. And of course, this is a Lycoming. So your right front, you got your number 1, number 2, number 3, and number 4. The lubrication for the rod journals, that flows, from in the main, and then there's a hole drilled in here off at an angle that goes up here to each of the crank pins. So the center main here, or that number 3 main, it supplies oil to number 2 and number 3 rod journals. One thing I'll point out right now so we don't forget about it, there's a test question that asks you, what is the location of the sludge tubes? And sludge tubes were put in early crankshafts. You can see the sludge tube in here if I'm aiming the camera good enough. And they're inserted in here. Back in the days before we had spin-on oil filters, we set this down for a second. Engines had oil screens on them. And the oil screen, it was okay, required more frequent oil changes and that sort of thing. And but the engines did have a problem of that sludge accumulating inside the engine if you went a long time on oil change and so on. So those sludge tubes were to help keep the sludge material from making it out to the rod bearings, because it is those rod bearings out there that living on those rod journals. That is one of the highest stress areas, because you got your cylinders pushing down and trying to rotate the crankshaft, and so if bearings were to go bad, that's typically the bearing that's going to go bad, is that connecting rod bearing. In fact, we've got a test question on that, so make sure you got pencil in hand, take some notes on it. There's what are the 3 classic symptoms of rod bearing failure? Okay, what are the 3 classic symptoms of rod bearing failure? Number 1, if you're in there tearing up that bearing, you're going to be creating a lot of friction and that sort of thing, and so that's going to create heat. So that tends to drive up your oil temperature. The second thing is you tend to lose oil pressure, because oil pressure in the engine is established in the oil gallery as it's flowing out to these points. You got a pump, and your oil pump looks like this. Back in the accessory case, you got an oil pump that is pumping the oil into the oil galleries and out to the various areas that do get pressurized. The main bearings, your valve lifter system, a few spots like that. But and then oil pressure is established by the fact there's a certain amount of resistance. Well, if we're tearing up a bearing and opening up the clearance, then not only is the oil getting hot, because as oil gets hot, it tends to thin out a little bit, and that's going to cause oil pressure to drop, as well as you've lost some of the resistance and don't have as high a backup or resistance to the oil flow, so the pressure goes down. So far we got high oil temperature, low oil pressure. And then the third one is kind of interesting, is that as that crankshaft is spinning around in the engine, oil that is spraying off of here is how the cylinders are lubricated. So that's another test question. How are cylinders lubricated on an aircraft engine? And it could either be sprayed, there could be like some little spray nozzles right off an oil gallery in the crankcase that shoots up into that cylinder, or it could be the splashy, so the test question says splash or sprayed oil up in the cylinder. Well, the piston rings that you have up, you got your oil control ring. Some cylinders do have scrapers, but not all. But that oil control ring is designed to handle a certain known quantity of oil. And so as it's out there spinning, and if more oil is flowing off of here, drop the oil pressure, high oil temperature, it's coming off of here, it's throwing more oil up into that combustion chamber, and we tend to burn oil. So high oil consumption. So it was interesting, one day I was just talking about this in class, and went back down to the office for break time, my phone rang, and it was a guy I had just overhauled an engine for. And he's on the phone saying that he's out flying, and he's got some, symptoms going on where he's got high oil temperature, his oil pressure is low, and he went through 2 quarts of oil in a very short time. And I thought, whoa, that sounds like a rod bearing failure going on. So then I gave him some additional instructions. Hey, go back, take your screen off the thing and see what you find in there. And of course he called back later and it's full of metal. Well, what happened was, this aircraft engine I put together for the guy was being designed for aerobatic competition. And I wanted him to get about 50 hours on the engine, and he only got 15 hours before he started rolling this thing around the sky, starving the engine of oil. And basically the cylinder got hot and kind of warped and was out of round, which then put more pressure on the piston, the connecting rod, trying to pull that piston in that warped cylinder up and down, which then put more pressure down here onto the crankshaft and ate out the rod bearing on it. That's another test question too that comes up, is you got your manifold air pressure gauge. I'll just kind of put it up there in front of you that way. So you've got a manifold air pressure gauge that, when the engine's at rest, it's at atmospheric pressure, it's 30, but when we start it up, that manifold pressure drops drops down to the 14 or so on that thing. And so there's a test question that asks, is it a high manifold pressure or a low manifold pressure that would put more pressure on the bearings, those rod bearings and stuff? And of course, it would be the higher pressure on you when you're putting it to it, or like in your car, stepping on the pedal. You would be exerting more pressure on those engine parts in there, the higher manifold air pressure. Okay. So this particular crankshaft here also, let's take one more look at it. You'll see how it's got a bent flange down there. And so this one was subjected to a propeller strike. And so one of the things, there's a test question that talks about when would you have to do a run out? So here is a picture of a crankshaft and the flange, and you'll see how your dial indicator is mounted down here right at the very outer edge. This one's had the drive bushings taken out of already, but you mount your dial indicator out there, and then of course you would spin the crankshaft flange and check to see how much run out there is. There is a question that gets thrown at you. If your dial indicator is reading +2, -3 thousandths, how much run out do you have? And of course that would be 5 thousandths total run out, because it's going +2, -3 for a total travel of 5 thousandths. Quick story. I've got several of these bent crankshafts around here. One of them was in our pilot program that I, of course, ended up having to do an engine overhaul for. Had a pretty good one because they had come in and landed and were pretty hot. And at the old school, it used to have a perimeter fencing was made of elevated, on stands, elevated railroad tracks. And they couldn't get stopped in time and ended up going right through where 2 railroad tie ends, and the prop came around and nailed the end of the railroad track. And so that was a very sudden stoppage. You can see that in the prop there, the damage to that. Subsequently bent the crankshaft flange and destroyed the engine, basically. They also caused some airframe damage too, because after the prop went through that elevated fence, then it went back and got the left wing strut on the thing and took that out on the airplane. So pretty significant damage for those guys that were landed a little bit hot one day. Okay, next thing I want to introduce you to is the term counterweights and dynamic dampeners. Okay, so first of all, a counterweight I introduced to you the other day, where when you have a engine, radial engine, that's got the master rod assembly, that's mounted out here on the crankshaft, then you have because that's offset and all that weight's out there to provide for basic static balance, you've got a counterweight. Okay, that is a counterweight. Okay, let me set this up here. Next thing is the term dynamic dampener. So the dynamic dampener that's right here has these movable weights on them. What we run into, the problem is you guys got to live in the test world. So test world, a counterweight provides for static balance. This dynamic dampener, which unfortunately the manufacturer quite often calls counterweights, but this dynamic dampener, it dampens those dynamic vibrations. In fact, that's a problem a little bit for our test questions. I'll get that out here for you. There is a test question. I don't know if you can see the print good enough on this, but down here it reads, which statement is correct regarding engine crankshafts? The correct answer to this one for 30-some years used to be the movable counterweights. So even in the test questions, they should say movable dynamic dampeners, but movable counterweights. And the answer used to be serve to reduce torsional vibration in an aircraft reciprocating engine. So if you have some testing software or something that tells you that is no longer the correct answer. The answer is now, because the book changed, and so where the FAA takes the answer from, the correct answer now up here, it says, movable counterweights serve to reduce dynamic vibrations in the engine. Okay, so that's what, maybe you take it and write in your notes or make note of that somehow, that the correct answer now. What does this dynamic dampener do? It serves to reduce the dynamic vibrations in the engine. That's the correct answer. Now, what this thing does is, maybe I'll kind of stand up over here and kind of explain this a little bit here. Do a little dance here in front of you kind of thing. So if I'm got my balance point fixed and I'm rigid, and someone were to come up and say push on my forehead, that I would go out of balance. I would tend to tip over. But if I add in some flexible joints kind of to the thing, then if somebody came up and pushed on my forehead and then I kind of just leaned my head back, the rest of me maintained my balance. So we've got something similar to that on this crankshaft. There's a certain amount of connecting rod thrust that hits that. And what this is all about, in order to save weight, these crankshafts are actually built a little too light. So they got little man's disease kind of thing going on here. They're not big enough to take the punch. And so then what we do is we punch that, basically, which would tend to want to throw it out of balance, but then the weight can actually move and maintain the balance. So that's how it's reducing those dynamic vibrations, they describe them. Okay. So there's another term I'm going to introduce to you on the topic of the dynamic dampeners, or sometimes called dynamic counterweights, is the word order. And we'll let you get that in your notes to help lock it into memory. The word order means the number of times per revolution that a vibration is occurring. You know, so they got special equipment set up on these machines to detect these vibrations, and then as they build these dampeners, you know, they got certain weight to them, and they got a certain parameter, a known parameter that they move to maintain that balance. Okay, so I'm going to turn on a screen here for you, and we'll talk a little bit more about that word order. Number of times per revolution a vibration is occurring. Let's make sure you can see that screen okay. Move you over a little bit there. Okay, so I'll just read it to the part that I want you to kind of, in case we can't see it very well in the picture, because it does tend to look a little blurry there. But and I'm going to change the wording of this a little bit, but it says counterweights. But what they really mean is dynamic dampeners. So dynamic dampeners are sold in matched pairs with the bushing installed. This is necessary to achieve their weight differences does not exceed 2 grams. And so what they're talking about is these guys have bushings inside of here. So these are all balanced out and to achieve that, so they don't exceed that 2 grams. The dynamic dampener order number designates the vibration order the counterweight is absorbing. If a vibration is occurring 6 times per revolution, then this dampener, it's going to be labeled a 6th order dampener, and it's supposed to go a certain location on the crankshaft. Similarly, if a vibration is occurring 5 times per revolution, then that counteracting dynamic dampener is then designated a 5th order number. So that gives you a little explanation if you're building up a crankshaft that's got the dampeners and stuff on it, that so you can kind of know where things go and certain part numbers and so on. One other thing we need to be aware of There's another term that's utilized in reference to these dynamic dampeners is dynamic counterweight system detuning. So as I mentioned to you, the dampeners are, certain spots, got certain weights, and so they are, if the engine is operated outside of the normal known parameters, then that can cause those dampeners to be moving places they're not supposed to be in the engine, and they'll actually start exceeding their limit. They'll actually start clanking. You get a rapid fire clanking on the side of the engine and starts excessive wear inside of the engine. And so that's called detuning of the dampener system. So quite often when companies, or training FBOs are for pilot training, if they're going to do twin engine training, you'll see there's just a certain types of airplanes they usually select because they don't want to pick out an aircraft that's got the dynamic dampeners in it, because they're doing things, like purposely shutting off one of the engines, simulating an engine out, so that the pilot's got to learn to fly a twin engine on single engine and all the emergency procedures. So they usually tend to want to stay away from those aircraft that would have engines with that dynamic dampeners in it that could get detuned during that process. So rapid throttle changes, putting an aircraft into a dive, feathering a propeller, and if I haven't introduced that to you yet, I can use my stubby little propeller here. Let me go ahead and turn this other screen back off. We don't need to see anything more about that detuning there. But a feather or a prop, normally you're going to be in so you got a low blade, you got your flat plane of rotation, and then you got a low blade angle, high blade angle, or a prop. If on a twin engine aircraft, they're required to have feathering capability, would go all the way 90 degrees and reduce that drag on the aircraft by the air easily flowing by. So you got feather. And then, so as I mentioned, sometimes just feathering a propeller could be possibly causing some detuning. And so you wouldn't want that to be recurring over and over and over as you would do possibly during some pilot flight training. So feather, high blade angle, low blade angle. So okay. This video is getting kind of long. I got to cover a couple more things here in this presentation. I think we're obviously going to have some part 1, part 2 things going on here with this guy. Next thing, bearings. As I mentioned to you before, the test question about what type of bearing provides the least amount of rolling friction, and that would be the ball bearing. And then you got roller bearings in engines, and then plain bearings. And that is the most common bearing you're going to run into and experience, of course, in our O320s you're working on, where that bearing, you got bearings that sit into the large ends of the crankshaft here. You've got your bearings that are inserted into the crankcase. And so those are your different types of bearings there. Let's see what else we want to mention here. Oh, so one of the things we got to do is we'll talk a little bit about rods again. I showed you a few things on the rods, but they talk about when an engine goes together, the rod numbers should always, so you can have a camshaft in the engine, and then down here's the crankshaft where the connecting rod's hooked onto, and they talk about how the rod numbers must always point away from the camshaft. That's a general rule, even in the automotive industry and so on. Rod position numbers always point away from the camshaft. So you'll see there's all sorts of fancy numbers etched on this, and these aren't the numbers they're talking about. There's also some nice casting numbers that are in here in the web of the connecting rod, and it's not those numbers. The numbers they're talking about is the numbers that get kind of pencil etched or vibrating penciled into the connect. So this one's got, you can probably barely see it in the picture, there's a 4 here and a 4 scratched into the rod cap. And they're supposed to go in a certain spot, and they make you then put the rod. So these numbers would have to point down away from that camshaft that was up here. That's for a couple of reasons. Remember how I talked about how the cylinders are lubricated by sprayed or splashed oil? In some cases, there might actually be a little hole that's drilled in the bottom of this that oil is spraying out, and it's drilled at an angle because this cylinder is going to be offset from this cylinder. So this connecting rod would be spraying oil into this cylinder. It might set either forward or aft of it in the engine. So if you got the rod number, you didn't think that was a very big deal. That rod might actually be in upside down. Now the squirter's squirting over there when it was supposed to be squirting this way, and so that could be an issue inside the engine. So rod numbers always point away from the camshaft. And then to help get that figured out, as we disassemble the crankcase section, one of the things we're going to do is we'll have taken the the crankcase apart, and then we're going to set that crankshaft back on its vertical stand, just like I showed you this crank here, and we are going to take a look at how those rod numbers are, because we've done some movement around of rods to achieve certain balances in the engine, and so we're going to want to track those rod numbers, because make sure that number 1 is where number 1 is supposed to be, and 2 and so on. Because what people tend to mess up on too is this rod, of course, has to point over here to number 1. This one has to point to number 2, but then number 3, people want a tendency to want to put the rod on this way, but in reality it is supposed to go over this way, because remember, number 1 and number 3 are on the right hand side of the engine, number 2 and number 4. So anyway, to make a long story short, that can be a little bit confusing. So when we go to reassemble the engine, so as we're disassembling it, we'll go through as a learning process in that to make sure we know how to put those connecting rods onto the crankshaft properly and in the right direction. Okay, so I think I'm going to end this particular video and get ready for part 2, since this one's getting kind of long.